Where we are going to do that.
Electronic products and computers have become an extremely important part of our daily lives. But what makes these products possible? What's behind the technology that makes our lives so much easier?
Beautiful tooth color filling, I think.
Fiber optic cameras, cell phones, televisions, and personal computers. All are operated by the silicon chips and printed circuit boards found inside. These powerful silicon chips allow us to explore outer space and dive into the intricate molecular structure of our own bodies. The complexity found inside a silicon chip, also known as an integrated circuit, is a monument to the advancement of science and the ingenuity of the chip's designers. In an area the size of a fingernail, a modern integrated circuit contains millions of tiny, densely packed switches known as transistors. These transistors are packed into units called circuit blocks. Under high magnification, we can see an electrical signal traveling through the circuit along miles of thin metal tracks. These convoluted tracks connect the tens of millions of transistors that make up a circuit. The signal travels through different layers of these tracks, making hundreds of thousands of turns within the chip circuitry. These microscopic structures are so small that 1,000 transistors can fit in the width of a human hair. Clearly, designing today's complex chips cannot be done by hand. Chip design would not be imaginable without the software and services from the industry known as electronic design automation. These companies are at the core of modern electronics. They provide chip and circuit board designers with the essential tools they need to make the most innovative products. Without EDA software, most of the devices we take for granted would either cost too much or simply not exist. Our world would be a very different place. To better understand EDA, let's look back at the first electronic computers. They required thousands of large vacuum tubes for their internal operations. The invention of the transistor in 1947 replaced the vacuum tube and ushered in the era of modern electronics. The demand for smaller, more reliable technology fueled the development of the integrated circuit in 1959. Transistors and other components could now be integrated on the surface of silicon wafers. If we look closely at a cross-section of a transistor, we can see how it acts like an electronic switch, turning on or off to control the signal's flow. This creates the zeros and ones of the digital language of computers. Since the mid-1960s, transistors have been made even smaller to increase their speed and to incorporate more functions within a single chip. In fact, industry pioneer Gordon Moore observed that the number of transistors in chips was doubling every 18 months. This fast-paced progress was producing enormous challenges for engineers who were then creating the designs by hand. As a result, chip designers developed the first software tools and began using computers to automate cumbersome manual design processes. This gave birth to what was then called computer-aided design. Soon, it was virtually impossible to design newer and better chips without newer and better versions of these software tools. By the early 1980s, a new industry had been born. Companies emerged that were committed to the development of this software. Chip designers now had the tools they needed to automate the schematic designs and simulate the signal's flow. By the mid-80s, the complexity of the designs reached new heights. To meet this challenge, new software was designed to introduce higher levels of abstraction. Designers could now work with the function performed by groups of transistors known as logic gates, and they could use a computer language rather than complex drawings to describe them. Computer-aided design was soon replaced by electronic design automation. Today, EDA provides software and services to the entire $1 trillion electronics industry and is an essential partner in its growth. EDA supplies the semiconductor industry with the software it needs to design chips, and it supplies the electronics industry with the software it needs to design printed circuit boards for its products. EDA is a highly technical software industry consisting of computer scientists and electrical engineers. Both disciplines are required to understand the electrical phenomena on the chips and to write the complex software that models them.
Hi, Charlie. How are you doing?
EDA engineers work closely with customers
with time enclosure, and we think we've got a big
and academic research programs to enrich what some now call the science of design. These collaborations are critical to the development of software tools. They allow the electronics industry to design systems with greater speed and efficiency, and they dramatically influence how quickly a product can reach its market, how fast it performs, and how complex its functions can be. By finding new ways to model and design ever smaller transistors and ever more complex systems, EDA has become an essential driver of technological progress. An EDA tool is a critical investment for a company. The result, however, is an electronic product that reaches millions. To understand the part EDA plays, let's see how designers go about transforming an idea into an actual product.
So I just got back from meeting with management in our architectural development meeting. This is the time frame that we put together for this project.
System architects first decide what the product will be and how it will function in the most abstract sense.
As you know, this is a telecommunications chip. It's going to be running on batteries.
EDA software helps them decide which functions to implement as either software or hardware. They determine the number of circuit boards needed and the type of integrated circuits that must be used. To design complex chips, architects first divide the design into large circuit blocks. Each block's design is then assigned to a group of engineers.
What I need you guys to do is kind of look at this and tell me which blocks you might want to own in this flow.
These engineers now use a hardware description language to describe the function of the millions of logic gates within the block. These textual phrases describe how the signals will move around the chip and how they will be read, written out, and stored as information in memory. A typical design may require tens of thousands of these descriptive lines. The description of each circuit block is verified to ensure that it will perform a specific function. Some blocks may have been used in previous designs or purchased from other companies. In the next step, sophisticated computers simulate the behavior of descriptive lines to show how they will work. This is a complex and lengthy process, but by modeling the signals before the chip is manufactured, designers can understand how they will behave and prevent costly mistakes. Design engineers then use other EDA tools to synthesize the design and convert the language into the basic building blocks of logic gates and transistors. Experienced designers make adjustments as necessary. They check specific requirements for speed, power consumption, and size to guarantee a chip's performance. This completes the first stage of design, where the original idea has been transformed into a circuit structure. The next stage begins with the placement of each block and its circuitry. Some blocks need to be near the edge of the chip, where they can connect to the outside world. Others need to be placed in the center, where they can communicate with each other. The shorter the distance, the faster a signal can reach its destination. Inside these blocks are the cells or logic gates, which EDA tools place and connect automatically. The routing tools now connect the tens of millions of these logic gates and individual transistors. These tracks must remain a minimum distance apart to prevent electrical signals from short-circuiting. Power tracks provide electricity to each of the logic gates. The green clock signal, shown here on the right, synchronizes the signals on the chip and must be routed so it reaches all the memory elements at the same time. Organizing these massive numbers of connections requires the use of several layers. A signal traveling along a track uses connecting points to move vertically and enter a new layer. This allows signals to cross each other. With up to 7 metal layers used in today's semiconductors, the design becomes an incredibly complicated three-dimensional puzzle. As a result, these designs must be carefully tested and analyzed to properly verify their functions. Finally, a drawing is created that describes the patterns that will be used to build and replicate the design on a silicon chip.
Information we already have in the network.
The design must be absolutely correct. One mistake could prove fatal to the system. The patterns are then precisely etched onto chrome-plated glass plates to create masks or stencils of the design. The masks are optically reduced to form the tiny patterns that are transferred across the silicon chip surface. Up to 20 masks may be needed to precisely create the many layers of materials that build the integrated circuits. The chips are then tested, packaged, and shipped to customers. As transistors approach the size of just a few atoms and chip complexity grows into the billions of transistors, the electronics industry will face tremendous demands. To meet this challenge, EDA software will be essential. EDA's close association with academia, which is exploring tomorrow's tools and products, provides exciting opportunities for a highly technical workforce. Working with customers, EDA researchers are creating the innovative tools designers need to reach new levels of product complexity. EDA's innovative software is driving the progress of electronics. Today, EDA is truly where electronics begins.